Okay, we're going to do another review. It's probably best if you kind of stay in kind of tight here. A lot of these slides are kind of marginal. I wanted to get back and redo them so that they're a little clearer, but hopefully they're all going to hold up for us. Let's see. We're going to be doing the review here. Now this is the third exam, which has the reputation of being the hardest. You know, the first one started off and the second one was harder. This is the hardest, your students will say. And hopefully you've been on top of the material as best you can, because it's not easy stuff. Look at all the stuff we've got: momentum and collisions. We're also going to deal with rotational motion, angular momentum, and even finish off with static. So it's like a lot of stuff here. And I'm going to try to help you sort some of this stuff out, and hopefully get as we kind of look over this stuff, you'll feel a little more comfortable with it. In case you're not feeling very comfortable, we'll give it a shot. So let's start off with just the basic idea of linear momentum, and we'll use that. Typically it gets used in things like collisions, but the idea, the definition of momentum, it's just defined. I don't know why they use the symbol P. Momentum starts with an M, but it kind of universally gets used. You'll see it in different books as you go through your studies. And it's defined as the mass times the velocity. It's a vector, just like velocity is a vector. In fact, they're in the same direction. Mass is just a scalar. These three little arrows, lines, just indicate this is just a definition. It's not something we tend to prove. Okay, and we've got this. Also, something that we'll kind of use later is the differential, or the time rate of change of the momentum. If we take the derivative of this and the mass stays the same, it's dv dt, that's going to be the acceleration. And you know that F equals ma, so this is just a little different way of casting the net force, is the time rate of change in the momentum. And or net force is equal to that time rate of change. Okay, now the idea is an important idea, and the idea of an impulse. And kind of the typical case would be something like a bat and a ball, where you strike the ball, your bat's in contact with the ball for just a short time, and then it's going to move, or we'll say change its momentum. Let's look at that. It's a relatively easy thing to show. The idea, the definition of the impulse is the integral of the force with respect to time. So if you think of a typical impulse like a bat striking a ball, where you have the force and the time, of course it's only in contact with the ball for a short time. There could be a real complicated interaction between the bat and the ball, and the force will typically spike and come back down. And the impulse is defined as the area under that, so we'd integrate that and get that area. Now, just looking at the math, it's not actually too scary. The net force, just F equals ma, that's the mass times the acceleration, and the acceleration is dv dt. These dt's can cancel, and then we're going to be integrating with respect to the velocity. The mass can come out, and then it's just really going to be mv final minus mv initial, which, according to our definition of momentum, is the final momentum minus the initial momentum, and that is the change in the momentum. So kind of summarizing that, the impulse, and kind of think of these three parts. That impulse is that force under the curve kind of thing, and it's equal to your change in momentum. Now, a lot of these things, we maybe don't know all the precise details. I've got this rather complicated looking thing, and it could be that this spike is very complicated and we don't need to know all the details about it. Very often in problems they'll talk about the average force. Well, if you got the force and it's varying, the idea of the average force would be some force that held over the same amount of time. Here'd be an example. Let's say we've got a spike here that goes up, comes back down, and we want to integrate under that. And we want to come up with some average force that if we had that average force for the same amount of time, we'd have the same effect on the change in the momentum. And so if you look at this just kind of graphically, if you sort of take this area and fill this in, take this and fill it in, we've got that idea of this average force times just delta t is the same as doing a complicated integral. And mostly what we'll be doing with impulse and collisions, we're not going to even bother to do this, but it's important that you have that basic idea. Okay, typical of what we'll get is something like a collision, where we get something like a couple balls that are going to come in and collide. I've got them coming in like this. Typically they come in, you know, they'll make some contact, and then they'll go flying off. Exactly how they come together and the angle that it comes at will determine which way they're going to go. And so usually in problems, some information has to be given as far as what's going to happen. But the idea that these two coming in, I've got momentum 1 initial and momentum 2 initial, they come in, they're going to have some contact here. And then while they're in contact, there's going to be Newton's third law, action and reaction. A force on one is going to be equal and opposite the force on the other. They're going to be existing in this safe state for as long as that collision happens. And so if we look at the idea here, if these forces are the same, and they're in contact for the same amount of time, we could say that the impulses are equal and opposite on these two balls, and it's going to cause a change in the momentum. Ball number 1 is going to come in, it's going to go flying off, it changes its momentum. This momentum comes in and it comes off in this direction. It too changes its momentum. Now, if we look at these impulses, one impulse is equal and opposite, so a minus impulse on the other. The impulse on one is the change in momentum of 1. The impulse on the other is a change in momentum 2. And so that's P1 final minus P1 initial equals minus P2 final, and then minus a minus P2 initial. And if we address these things with moving all the final terms over to one side and the initial terms on to the other side, we have P1 final plus P2 final is equal to P1 initial plus P2 initial. And this is what we can say is the final momentum, and we talk about this as being the final momentum of the system, the two of them taken together. And that should equal the initial momentum of the system. Now, we often, and in fact we call this thing momentum or conservation of momentum. Momentum is conserved for the system. Individually, they don't have conservation of momentum. This one was coming in this way and it goes off like that, and this one's coming in and like that. So they both change in momentum, but these changes are always equal and opposite, and so the overall momentum of the system, again, is conserved. Now, there can be additional facts about this collision. I've got sort of like these are, racquetballs that are going to bounce off of one another. One thing that sometimes they call it an elastic collision. Now, elastic collisions are very special in that they bounce off of one another. The idea is that they don't lose any energy to heat. A typical elastic collision would be, let's say I take this ball and I just drop it. Well, was that an elastic collision with the floor? No. Where would it come up about this high? So if I started this, it's got mgh, and if it only gets up, doesn't even get off the table here, it's maybe got maybe half the energy that it started with. A true elastic collision, if this thing is going to have an elastic collision with the floor, it's going to bounce off the floor and it's going to come right back to my hand. So I like calling these semi-elastic because but the problem would have to state that it's an elastic collision. And then you add up the kinetic energies of these balls, or the whole system, initially is equal to the sum of the final kinetic energies. And so we'll look at these type of things. Something that's a totally inelastic collision, would be something like a ball of clay. I just drop it and it splats on the ground and it doesn't bounce at all. That's a completely inelastic collision. But what's interesting here, if it's an inelastic collision, a lot of heat is generated. Well, let's get to some examples here before I try to overspeak it here. Let's look at just kind of a simple problem. This is one of the practice problems off of an exam here. And I realize it's kind of difficult to read some of this stuff. 12-gram bullet is traveling with a speed of 400 meters per second, coming in here and hits and passes through. So it's going to rip through this 0.75 block of wood that's sitting on the corner of the table. After the collision, the bullet is traveling with the same direction with a speed of 100 meters per second. So it's slowed down considerably. And if the block of wood is 1.4 meters above the floor, how far from the edge of the table does the block hit the floor? So this bullet's going to come through. It's going to rip through this thing and set the block in motion. Now, in terms of doing problems with conservation of energy, tend to think of a kind of a before picture and an after picture. And the actual collision itself, as this bullet rips through this block of wood, is inelastic. There's a lot of friction, there's heat generated, and so we're going to lose that energy to heat. But momentum is still conserved. I can still make use of that. So we don't talk about the actual collision itself. We focus the before and the after picture, and that's what we want to do. You kind of imagine like you're going to take a snapshot of this, and so you got 400 meters per second of this bullet. This thing's at rest. So we can talk about the initial momentum of the system, the two things together. We've got that bullet as well as the speed, 400 meters per second. The block of wood, of course, is just sitting there, so it's got zero velocity. And so I can quickly crunch the numbers, and you can see it's 4.8 kilogram meters per second is the units. We don't have a separate unit for momentum. Then as it rips through here, I need to find out what the speed of this block is, because that speed of the block is going to go flying off the table, and the faster it's moving, the further out it's going to hit. So we need to solve for that. The bullet is slowed down, and as it rips through here, that is considered what we would consider a collision. So we've got them both now in motion. P final would be that same bullet. It's now slowed down to 100 meters per second, but we also have the block of wood moving. I don't know what its speed is. I'll just call it speed V. And so we can kind of simplify that. And then conservation of momentum, we would set the initial momentum equal to the final momentum. Go ahead and set that equal. And then we can solve for V. So it's relatively simple algebra. And I come up with 4.8 meters per second. Okay, but we're not done with the problem. And this kind of exemplifies what can happen now at this time in the course. This would be something that we'd look at in the very first exam. So we're kind of going all the way back. In a sense, the whole semester is included here. As you recall, the projectile part. This stuff is going to be on the final for sure, and could be here on this one. It's in this one. Using the idea of the linear kinematics, that keep in mind that for this projectile, hopefully this is you remember this, that the time that it's in the air would be the same as if I just dropped something like a stone from the height of the table down to the floor. And I can get the time that it's in the air, and I do that in the y direction. Initially, this block is just headed in the x direction, so there's no velocity in the y. Gravity, of course, is pulling down on it with a negative, and it's up off the floor 1.4 meters, and setting that equal, I can solve for the time that it's going to be in the air. During that time that it's in the air, it's traveling with this speed, 4.8 meters per second, for that time, and that would tell us how far it's going to get in the x direction as it hits the floor. So again, all of this stuff, the whole semester is kind of on our shoulders for doing these kind of problems. So be one example. Here's another simple example, relatively simple. We've got a 25-gram bullet traveling 300 meters per second. It's coming in. It's going to hit a stationary 200-gram tin can, and the bullet will be deflected at 20 degrees. And the can recoils off here at 40 degrees. And he doesn't ask how fast they're going to be traveling, but he asks for how much heat is created in the collision. So that indicates that this is an inelastic collision. So even though they bounce off of one another, this is just a case of, again, what I'd call a semi-elastic collision. We're going to lose some kinetic energy, and that's going to end up going into heat. But for this first part, we're going to take a look at the momentum. Initial momentum in the x direction will equal the final momentum of the x direction. Also, these are going to take off in both the y direction, and so we also have the initial momentum in the y will equal the final momentum in the y. So now it's a matter of putting this together. Our before picture is this bullet traveling at 300 meters per second, headed towards the tin can, which has 0 velocity. They collide, and I've got the bullet is going to go off with some velocity. I'm not sure what it is, so I'll just pull it v sub b for the bullet. It does go off, he tells us, at 20 degrees. And we've got the tin can, 0.2 times the velocity of the can, and it's going off cosine 40 degrees. Okay, both of these are in the plus x direction. And so I've got really two unknowns. I need another equation, but I've got this other equation in the y. The initial momentum of the y is equal to the final momentum in the y. The bullet was coming in strictly in the x direction, so initially there's no momentum in the y direction. After the bullet hits and scatters the can, we've got them both moving. The bullet gets deflected up sine 20 degrees. Again, I don't know what the velocity of the bullet is. I'll just put that in as v sub b. The tin can, though, does get sent in the y direction, so I'll call that down as negative. That'd be its mass times the velocity of the can times the sine of 40 degrees. So we can simplify that. So I've got really two equations and two unknowns, the velocity of the bullet and the velocity of the can. Now, I don't have all the details. I trust that you're sophisticated enough in your math to be able to solve for that. And I want to just kind of lay the pieces of the puzzle out so that you have kind of the big picture of what you need to do. So you've got these two, and we'll bring them together, and we should be able to take these two equations and solve for our unknowns, the velocity of the can and the velocity of the bullet. So I've got my results. You should work these problems for yourself and convince yourself. I think I haven't made a mistake here. Nobody's called on me on it yet. So I think these are right for their velocities. But that's not what he asked. He asked how much heat was created in the collision. So the idea, we'll take a look at that from the energy principle. Initially, the bullet came in with a certain kinetic energy, and it's going to go off. There's going to be some final kinetic energy, and he's suggesting also that there's going to be some heat loss to heat. So we want to solve for the heat that's generated. So our initial energy, just kinetic. Final is both kinetic and also heat energy that's generated. So I'll take my results. I did need to find these, even though he's not asking for them, that the kinetic energy initial is just that bullet traveling at 300, and the final kinetic energy is that bullet now traveling at 223, and then plus also the kinetic energy of the can. So we've got both of these things moving with kinetic energy, and then we're left over with the heat. And so when I set these things equal, I can go ahead and solve for the heat, and I've got this many joules of energy that are lost to heat. And that would hopefully answer that. So, Okay, let's go to something, and I'm going to be doing some more examples using conservation of momentum. It gets tied into some other problems later, but let's kind of go with the basics of where we're going. And an important idea that runs along with conservation of momentum is the idea of center of mass. And let's just start with kind of the definition of it. We talk about the center of mass of something. I've got some particles, or they could be actually spheres. They could be other objects. I've got kind of three of them just kind of illustrated here, and the idea that they could be little point particles. If they happen to be something like a sphere or a disk, we would use the center mass of them, and we just say, well, the center mass just from symmetry has to be in the center. So I can assemble things, either point masses or individual things, in terms of getting the center of mass of this system of particles. I've got three of them. Sort of makes sense the center of mass is somewhere between them, but we need to locate it more precisely. And we can locate it both in the x direction. We'll find the x center of mass as well as the y center of mass. And also this extends into the z direction, coming out at you, z center of mass. So we define it this way. It's not immediately apparent why we would even care about defining it. The x center of mass is the individual mass particles times whatever x position they have, and we sum those up and divide by the sum of all the masses, or the total mass. We can do the same thing in the y direction and also in the z direction. In terms of doing this as a problem, when you're going to do this and set up a setup for this, you need to choose a coordinate system. And it really doesn't matter where you put the origin to your coordinate system. Think of the coordinate system almost like a ruler, where you can move it around, you can put it down wherever you want, and you're going to be taking all your measurements from there. So if you have, let's say, an x and a y axis, and you just say, I'm going to choose, this is my origin, and you have that choice of where you want to measure from, and we'd make all our measurements from this point, and our final conclusion as far as the x center of mass and the y center of mass and the z center of mass is going to be all measured relative to that chosen origin. So hopefully you've got this idea a bit. So okay, so now what we can do is combine the x center of mass, the y center of mass, and I didn't put it up here, but we could also write the z center of mass, same basic prescription. And if we do that and put that in for the x, the y, and the z, we can have a position of the center of mass, both in the x and the y and the z, and the position vector for that center of mass is measured right from the origin, goes right out to this point. And we can look at this as a vector. It's helpful. X, y, and z components. And each of these has an m sub I, the m sub ith term is in both of these terms as well as the z term. I can take that out as well as the sum of the total masses I should be able to take out. The thing that I'm going to be left behind with is this x sub I plus y sub I plus z sub I. And then the idea of bringing this out, we can express this whole thing. It looks a lot like these, except they're in terms of the vectors. We can have this one's position vector, R1 up here, R2, R3. If we go ahead and add those vectors, we'll come up with where the center of mass is. So this is kind of the general form of this. And again, summing up all the masses is just what we'll call the total mass of the system. So this total mass of the system I can bring over to the other side, and this is kind of a useful way of thinking of the center of mass. The mass times the position of the center of mass is just equal to the mass of the individual particles and their position. So hopefully this is a little bit more visual than something just as abstract as that statement. we can, this has some big consequences. So this is one reason we wanted to find the center of mass. So the position of the R center of mass is just m times R sub I over m sub I. This is the total mass. And if I bring the total mass over to the other side, where I've got the total mass times the position of the center of mass is equal to the individual masses in their positions, all just summed up. And if I take a derivative with respect to time, the total mass isn't going to change, but the position of the center of mass can change. And we take the derivative of that. We go in and on this side of the equation, we take the derivative. Mass doesn't change, but the derivative of that changes. And that's the mass times the derivative of that position vector. Okay, again, this is kind of abstract, but if you think about that, this is going to be the velocity of the center of mass. So the total mass times the velocity of the center of mass is the momentum of the center of mass, is equal to the sum of the individual momentums of all the particles or pieces of this, just the summing them up. So the total momentum of the system is just equal to the sum of the individual momentums. We can take another derivative. We take the derivative with the velocity of center of mass with respect to the time. That's the acceleration of the center of mass. And we take the derivative of these individual velocities, and those are just going to be the individual accelerations of those particles. And that's going to be F equals ma. That's going to be equal to the individual forces on those. And we would sum up all those individual forces, and that should equal the net force. So from that basic definition, we're starting to get into a little more comfortable territory, hopefully. I realize this is still kind of abstract here. But this is really Newton's second law, F equals ma. We're now getting a little more sophistication that this net force is equal to m, and the a is actually the acceleration of the center of mass. That's why it's so important. This would be true, Dr. Young, I think, does this one as well as a hammer, okay, that its center of mass is, well, it's about here with this red dot. And the idea that if I want to do something like throw this through the air, it's going to go off and go through a path through space that's going to do this kind of thing. It's going to be rotating as well as translating. Now, when we talk about the acceleration, that acceleration is the center of mass. So if this thing is traveling through space here, maybe on a parabolic path, it is the center of mass that's going to travel on a smooth parabola, and then as it goes there, it's going to then be rotating around that point. So it allows us to take what you would think would be an extremely complicated path through space and break it down into simply the motion of the center of the mass as well as the rotation around the center of mass. And of course, we'll get to that rotation part in a little bit. I'm just kind of focusing on this. So this is sort of a kind of a more precise definition of Newton's second law. F equals ma, but that a is specifically referring to the center of mass. Now, if that net force happens to be zero, and this is going to be an important test, if it's zero, then the mass times the total velocity of the center of mass is equal, of course, to the sum of the individual momentums, and that should be some constant. Since if I take the derivative of this, that would be zero, and derivative of a constant is zero. So this is essentially a statement of conservation of momentum. The mass times the velocity for the whole thing, that is the momentum of the whole system, is equal to the sum of the individual momentums of all the pieces. So a lot of stuff here, and it's generalized, and it does again, starting from this basic definition, we derive kind of the basics of mechanics. So kind of looking at this kind of backwards now. Okay, We'll come back to this a little more. We'll do it several times where we'll take a look at the idea of conservation of momentum. But now let's get into this idea of, I'm going to set something in motion, can also take, along with that, a circular motion. So let's just talk about circular motion in general. Let's say you just have a particle that's going to be going around in a circle. And it's going to trace out, let's say, a path S. This would be just the arc length along that circle. You can imagine taking a tape measure and just wrapping it around this part and measuring that distance. And compare it to, I'm going to superimpose on that the unit circle, because we want to relate this to circular functions. I'm going to put a unit circle on there. A unit circle, of course, is at a radius of 1. And there's going to be an arc. This arc is going to mirror an arc that's on the unit circle, or sort of think of the shadow of this back projected onto the unit circle. This is what we mean by theta in radians. I have the subscript radians to remind us. We have to use radians for this. We can't use degrees, because this represents the arc on the unit circle. Then we can look at the simple proportion between these. So these are like pieces of the pie here. They're similar. They have the same basic shape, different dimensions. But we can say that this arc S is to R, the radius of the path that it's taking, has got to be equal to theta in radians as to its radius, which is just 1. And so that leads to a simple idea that the arc that they travel through as you move through a certain number of degrees is just going to be equal to r times that theta. And again, that theta has to be in radians for this scheme to work. If you want to get something like tangential velocity would you be moving on this circle. Tangent to it would be the direction of it if it's going to take a circular path. We've dealt with circular motion previously, and we call that the tangential velocity. And that should be equal to if we take just ds dt, taking the derivative, we take the derivative over here. The r isn't going to change, but the angle will, so that's d theta dt. And we typically use this symbol, this is the Greek letter omega, to represent the time rate of change of theta with respect to time. So I can take this, I take the derivative, ds dt is the velocity, tangential velocity, is equal to r times the angular velocity. Lots of stuff to remember, and hopefully this is coming and it will be more comfortable for you as you dig into this a little deeper. If we want to go one more step and get the tangential acceleration, I can do that by taking the derivative of this again with respect to time. So the tangential acceleration is going to be r times d omega dt. That we use the Greek letter alpha to represent what we'll call the angular velocity. And so we've got the tangential acceleration is equal to r times the angular acceleration. Okay, that's the tangential part. We dealt with this before, like on circular motion, where we get some kind of tangential acceleration. That's going to cause the thing to either speed up, or if we run it the other direction, we can cause it to slow down. And also, don't forget there is an acceleration in the radial, or really centripetal direction, into the center of the curve that's always going to be v tangential squared over r. So this should be a reminder of what we had done earlier with circular motion. Okay, so for circular motion, trying to keep all these terms straight, I admit, is difficult, and then applying them on top of that can be equally difficult. We are going to do something very similar to what we did very early in the course. We did linear kinematics, and we dealt with the case where the acceleration was constant. And we know that the acceleration is dv dt, and so what did we do? We integrated, anti-differentiated or integrated. We got an expression, at plus some constant. That constant would be when t is equal to 0, v is equal to v naught. We can get the velocity is dx dt, so we can get the x position. By integrating this one more time, we end up with a 1/2 at squared plus v naught t plus, when t is equal to 0, these terms go out, the position x is equal to x naught. We can eliminate t between them with another expression. So this should be a kind of a review from what we had done. And we can relate this to the tangential acceleration for circular motion takes the place of the acceleration. Tangential acceleration, you would just speed up as you go around this thing. You are going to be traveling in a circle. You can think of the S as being like a tape measure that's wrapped around this. So we can look at circular kinematics, very similar to this. Once you have this down, hopefully you can see this relatively clearly. Usually this is in the x direction. Instead of x, we're using s. The arc is going around that circle. But we can still go ahead and use the same basic equations. And once you have derived these, you should be able to come to these. And then we can go back and use these relationships. AT is equal to R times alpha. So if I just take this and divide by R, I will get this, this will be alpha. Instead of tangential acceleration, tangential was R times omega. I can divide out an R through here and just get this in terms of omega. The S I can divide through by R, and that's going to just be this angle theta. So we can translate it this way, or we could do something similar to what we did over here, where we said the angular acceleration is a constant, and then I take the integral of that. Looks a little strange with all these Greek letters, but it's really mirroring this. And if you look at this expression, think instead of, well, in linear terms we have velocity, angular terms we have an omega. You can just replace this with an omega. Instead of an acceleration, we put in an alpha. Instead of v naught would be v naught, well, it would be tangential, or excuse me, omega naught would be the tangential related to the tangential velocity. So you need to play with these a little bit. They get used in some of the homework problems, and they could immediately come up on the exam.
Can I ask one small
Yes.
question? The A sub r, is that also equal to r times omega squared?
Oh, no. Okay, good point. Yeah, all these other things are really along this direction. So like v tangential is in this direction.
Yeah.
The direction of A sub r is really into the center. And remember, if you recall from, let's say it was in the way back to the first test, where we had kind of two components to the acceleration. We had a tangential term, which caused the particle to speed up or slow down. And then we have this centripetal or radial term that's into the center. This deflects it into a circular path. So this doesn't speed it up or slow it down, but it is that deflection. And its direction is into the center. And so it's kind of a little, remember this too. Okay? Okay, yeah, thanks. And yeah, feel free to kind of interject if there's things. I know we've got so much material. I know we're kind of flying along, and hopefully you can hang on. Okay, now let's start with something like, we call it a rigid body rotation. That is, it has a particular shape. It's typically a solid. And it's going to rotate around some point. And I've got sort of just an arbitrary, it could be like a sheet of steel or something that is going to, has a pin in it. And it's going to be able to rotate. Now we can use this idea that we developed in the previous slide to start to talk about building this problem. Let's start with the idea of, well, let's say I've got this thing. It's rotating with some omega, And there's out to individual pieces. Imagine chopping this thing up if we're going to do an integration, which we're not going to do, but the idea we chop it up into a bunch of little pieces. They have their individual little masses, and as this thing rotates, they're going to be traveling different velocities depending how close they are to the point of contact. If you're the axis, if this distance is small, this velocity is going to be small. Keep in mind that velocity is going to be equal to r times this omega, this angular velocity, and this velocity is going to be a little more, it's a little further away. This one's further away yet, and so its velocity is going to be greater. All those little pieces have different velocities, but the importance of what we just derived there was the idea of the angular velocity should be the same for all of them. The omega is just different. So v of any individual terms is just that, r of that term times omega. So let's say we want to do something like get the kinetic energy of this thing. It doesn't matter, what direction. These directions are all perpendicular to the r's. They're traveling around. And so we could talk about the kinetic energy. That's going to be the sum of all the individual kinetic energies of all the little pieces, 1/2 m v sub I squared. But v sub I is going to be varying for all of them. So I can put in r sub I times omega in for v sub I. Got that? And then we can do some things, we can factor some things out. This is a sum of, we're going to just add all the kinetic energies of the pieces. I take that 1/2, I can factor that out. And the convenience of omega, I can square r squared and omega squared. I can take the omega out as well, since these are the same for every term. And then what's left over is going to be the sum of all the individual masses in the radii. And this is going to depend on what kind of shape we choose, but this pattern is going to reappear a number of times during this review. Is something, we give a name to this. What's that called? Moment of inertia. A little bit different than standard inertia. Standard inertia was mass, And do you know what mass is? Nobody's really sure what mass is. We do know that it has this property of inertia, where if you've got something at rest, it tends to stay at rest. As you give it a push, you can start to accelerate, but it resists that motion. And once it's at rest, it wants to stay at rest. After it's in motion, it has that motion, and it's difficult to stop it, the bigger the mass. This kind of thing, the moment of inertia, or rotational inertia is another way to describe that, has the same basic form that the larger this is, the more inertia it has, the more it has a resistance to an acceleration. Anyway, so we're going to just define this, call it I, the moment of inertia, and it's the sum of the individual pieces times their radii squared. It's kind of the whole geometry of this piece. And then when I put that together, get that I put it in with this, I can arrange it in this way. The kinetic energy is equal to 1/2 I, the moment of inertia, times omega squared. Again, consider the moment of inertia is just the kind of the dimensions of this object kind of summarized in there. And it's whatever omega we want to rotate that thing with, that is going to lead to a kinetic energy. Now, keeping all this stuff straight is not easy. Compare that to ordinary kinetic energy, 1/2 mv squared, where instead of the mass, we're going to use the moment of inertia, or rotational inertia. Instead of the velocity squared, we're going to use omega. It's important to realize that this was really derived from this 1/2 mv squared. So there's really nothing new physically. We're just kind of doing the math a little bit differently in the way we're doing that. if you have a problem, since this is made up of the sum of all the individual kinetic energies of the pieces, if you got something else that's all part of the problem and it's going at some different velocity, you can go ahead and use a mix and match of these, since this automatically came from this. So if we've got a complicated system, we just add up all the kinetic energies. You can use 1/2 mv squared if that's convenient, or in the case of a rigid body, usually this is more convenient to use. So we'll be making use of both of those. Okay, let's do a little example of the idea of the moment of inertia. We're going to we sum these individually, but we may have to have an extended object. Like this is going to be that of a rod. We're going to rotate around the center of mass. And how we would calculate that, this is one of the practice problems. And in integral form, we're going to break this thing up into a bunch of little pieces. I've got instead of x, I call this r, and this is going to be a little dr, some arbitrarily small piece. And that's going to be some differential mass, so that's going to be a dm. So kind of writing these in reverse order, since this mass of this piece is going to be small, I'll put it over here and make it differential. And then the r is going to be out front here, r squared. And so this is sort of saying this, but doing it again in integral form so we can integrate this thing. So I'm going to take this rod. We want to rotate it around this center. So we chop this thing up into a bunch of pieces. I've got one piece here. I'm going to call it dm. It's got a length dr. And it's going to be out here at position r. And as this thing rotates, of course, this piece is going to go in a circle. Pieces that are in closer are going to go in tighter circles, or further away are going to get bigger. And so we need to integrate or add up all these pieces together to get the total moment of inertia. Now, a lot of ways of doing the math here, but this is kind of the simplest one I can think of for looking at this and saying, well, if this is dr, I need to come up with dm. And I can do that with kind of a simple ratio. I can say the mass of the whole stick, big M, is to the length of the whole stick, as this mass, tiny little mass, is to its tiny little length. So looking at that like that. And so dm, I'm going to bring the dr over here. So dm is equal to m over l times dr. And you can kind of reason it this way. Or if you have been exposed to the idea that m over l is the mass per unit length, so we can take the mass per unit length times the length of dr and come up with dm. You could write this one straight off. You wouldn't have to do this first. But hopefully you can see that a bit. So now it's a matter of putting these things together. I want to use this as my integral form, r squared dm. And I need to replace the dm. I'm going to, since we're going to be rotating around the center, I'm going to integrate from minus L over 2, that's back here, out to plus L over 2. Or, as you probably know from your calculus, for the idea that this being symmetric, we could say this is 2 and then go from 0 to L over 2, just simplifying that. Inside the integral, we've got r squared. dm is, again, m over L dr. And then we need to integrate. We can take the m over L out along with the 2. And then we're going to be integrating. We're going to have an r squared dr, which is going to integrate to an r cubed over 3. Putting in our limits, L over 2, we're going to get 2/3 m over L, L cubed over 8. The 2 and the 8 make 4, and this is a 12. And I think you can piece it together. This is going to be m. One of these l's goes out, so we end up with L squared. Should always kind of have these units of mass times distance squared. And so the moment of inertia for a thin rod is 1/12 ml squared. So Dr. Young has there was a time where I could guarantee you that you're going to have one of these type of problems on the exam. He's gotten away from it a bit. You don't see it as much, but it's not impossible that he could ask that. I've got another one like a disk. Some of these derivations are really hairy, so we won't get into them, but this is a good example of one. Typically on the exam, he's going to tell you the various shapes, or what he has done is, like the chapter 10, you have a table of different shapes and what their moments of inertia are. Invariably, they're going to be about the center of mass, most of them. The table you have in chapter 10 has two things for the rod. One about its center, 1/12 ml squared. It also has one about the end point. Instead of rotating it around the center, it's going to rotate it maybe around the end. And so things are going to change a little bit. But whether you use the table or not, one thing that he really likes is the parallel axis theorem. So you want to be ready for that. And it's relatively simple to apply, and we're going to be needing it to do some of the problems that we're going to be looking at. The idea that, let's say I want to rotate around this axis. I'll just call this point P. I want to get the I about point P. And the parallel axis theorem says that, okay, the I about point P, rotating by parallel axis, what do we mean? We have the center of mass where we could rotate it around that, so the axis is this way. Or if we're going to rotate it around the end, the axis, again, is parallel. They're both pointing out. That's where the parallel part comes in. And then this thing is going to revolve around point P. Now, I could do this as the integral. Actually, just on the previous one, I could have integrated from 0 out to L, and I'll get the same result. But again, I want to illustrate this idea of the parallel axis theorem. It's all dependent that you know what the I of the center of mass is. And then the idea, I about some other point that's other than the center of mass is back here, is I about the center plus the whole mass of the whole stick, as though you could crunch it down and have it a single point particle at the center of mass itself. There's going to be a distance from the center of mass out to where we're going to move the new axis. In this case, it's going to be, that distance will be just L over 2, half the length. So I'll put in for D, we'll put L over 2. And so we use that 1/12 ml squared. We can add to it ml over 2. We square this. This is going to become a 4. And we're going to get a 1/12 plus a 1/4 ml squared. And this is going to be, well, you can do the math here and convince yourself that this is going to be 4/12 or 1/3 ml squared. So that's a greater moment of inertia. The idea is that it would take more to get it moving. It's easier to get something to rotate around its center of mass than it is to go all the way out here and get it to rotate from this point. So a greater moment of inertia. Okay, let's, I've got another one here, but I think in the interest of time, we've got a lot of ground to cover. You can maybe do this on your own, is the moment of inertia of a disk. Maybe I'll just point out kind of the high points of this. The idea that you're going to chop it up into a bunch of rings, and you're going to stack up all these rings to form a disk that you're going to rotate around. A disk maybe has some thickness to it, could have any kind of thickness. It's got some mass to it. Then the idea that the differential volume, that is going to be the volume of this ring. Think of this as a real thin little piece, a little dr is the thickness on this. It wraps around. And if you imagine taking that thing and slicing it and then laying it open flat, this circular part would be one dimension. So 2 pi r would be the circumference of that thing. Times dr would be the width of that, and it's going to have a length of t, so this should be t times 2 pi r dr. You want to get used to this. You will be seeing this kind of stuff if you haven't seen it already, like in calculus. This is going to be the small differential volume. By differential, I mean really tiny. And The mass of this thing would be the density times dV. Put that in. And then we still go back to this integral form. We've got this dm is going to be the density of the material times the volume. That volume is going to be here. And we've got some things we can take out. We're going to have an r cubed that's going to integrate. I don't like to let you kind of do this for yourself. And then we come up with a relatively simple answer. And you've been doing a lot of problems. Disks get used a lot. So you probably pretty well know already it's a 1/2 mr squared. But that is the rotational moment of inertia around the center of this thing. Very often in problems we take it off center, and we'll be doing some here as well. So thought I'd kind of let you know that and let you pick through that energy yourself. Okay, let's do a simple energy methods example. We've got a disk that's it's got an axis here, so somehow this is fixed. You know, it's not going to fall. It's allowed to spin. This is a frictionless axis, and we've got a cord that's wrapped around here and attached to a mass. And we're going to start this from rest. This is fixed, but this mass can fall. And as it falls, it's going to, of course, pick up kinetic energy as it drops and also get this thing to start rotating. So we can look at the energy. It's going to start from rest, so the kinetic energy is 0. I'm thinking, let's make this 0 potential energy. So it's up here. That mass has mgh is its energy. That's the initial energy. The final energy as this thing falls a distance h, once it gets down here, its potential is back to 0. And so the final energy is just these two things in motion. 1/2 mv squared represents the kinetic energy of this piece, and 1/2 I omega squared would be the rotational part. So you see how I'm kind of mixing and matching these two, whatever's convenient. I'll use 1/2 mv squared for the rigid body. This is the part that's convenient. You can, and I'm using a disk for the pulley as often it gets done, so it's a 1/2 mr squared. So I've got a half out here as well as one inside here for I. And V is going to be V over R. We'll put that in. We can square that. Now, one pattern that typically shows here, this R squared here, and when we square this, R squared, the R squareds drop out, and we end up with a 1/2 big M for the, I have for the disk, V squared plus the kinetic energy of that. And we can factor out the V squared, and we can look at these terms and even get the velocity. I just have these as symbols, but again, this is 1/2 this mass, and this is 1/4 of that mass as it drops. This is going to be the velocity of this piece as it drops. So hopefully that makes sense. Okay, now let's do a problem that he has been doing a great deal lately. And let's start it just kind of simple. The idea that you could have, let's say, something like a meter stick. In fact, I think he uses a meter stick in this example. And it's attached at one end, so somehow it's attached to the wall. And it's going to, we're going to drop it, and it's going to swing down. And the question is, he wants to know how fast, when it gets vertical, how fast is the tip of this thing moving? Okay, so that's the problem. And so there's some subtlety in this problem, though. When we start up here, okay, we're going to, and we'll use energy as an example. I'm going to make the very bottom here, I'm going to make that gravitational potential energy 0. So we can look at the potential energy initially. It's at rest, so there's no kinetic energy, just gravitational potential energy, mg, and I have it times L, the length of this thing, okay, which is whatever length the stick is, I'm going up, and all these little bits of matter that are part of the stick are all up there at the same height. And so that's going to be mg, and again, up a distance L. When we release it, it's going to swing down, and at the bottom, It should pick up, it's going to have its kinetic energy, actually maximum kinetic energy as it swings through the bottom. And as it swings through the bottom is, what is the potential energy? Yeah, is it 0? Okay, this is kind of tricky if you think about it. The natural response is, oh, we're back at the bottom, that's 0. The problem is this piece right here dropped all the way down here, and it is down at 0. But what about this piece? Did it drop at all? It's still up there at this height. Or if I take a piece here, it's going to drop down here. It's not going to fall the whole distance. So as this stick swings down here and it's at the bottom, this piece is still sticking up here. So what do we do about that? Now, when you gain some experience, you're gonna see this better. But let me point out something here. For this vertical stick, we want to get the potential energy of the vertical stick. Keep in mind that all the little bits, and I'm going to chop it up into a bunch of pieces. This is a typical piece here. It's got its mass dm, and of course it's got a length dy. We'll be able to get the size of that. But it's sitting up here at a distance y, so it's going to be its mass dm times this y. And in fact, it's going to have a little bit of kinetic, a little potential energy. du sub g is going to be equal to the mass of that piece, which is going to be a tiny little mass, dm, times g, times its position, y. And as in the other problem where dm, the mass of that piece, is m over l dy, what we can do to take this potential energy, to get the total potential energy, we need to integrate it over the whole stick. du sub g, we're going to integrate this expression, so I'm going to put that inside here. I'm integrating with respect to y. A lot of these constants come out, but I'm left with a y. It's inside here. I kind of should have broke this into another step here. But we've got a y. When we integrate the y, that's going to become a y squared over 2. We need to integrate from 0 to L, so the whole length of the stick. And we can get the potential energy due to gravity is going to be equal to mg L over 2 is the result. Okay, now, so the idea is, rather than integrate this, and I'm not suggesting you do this on the exam, but you should know the strategy to it, that when we do integrate all these together, it's the same as if I took the total mass of the stick times g at a position of L over 2. So crunch all the stick down to a little point mass. It's sitting up here. That is the potential energy of that piece. Is the same as for the whole stick. This is another reason why center of mass is important. Yes?
So instead of going through all the integration, can we just find the center of mass?
That's right. Yeah, and that's the point I'm trying to make now is, yeah, don't do this. Having seen this, hopefully you have an appreciation why you want to do this, because it's an easy trap to fall into, saying, oh, that's 0 here. It is actually got a potential energy as though the whole stick is there. And yeah, as far as doing problems, he's going to be totally fine. You're not going to do this. You're just going to say, center of mass. And measuring for the potential energy, I want to use the position of the center of mass to get my h. So mgh, that h is the distance to the center of mass. Yeah?
So if instead of a meter stick, if it was just like a ball on the end of a string, then in that case we could say the potential energy is 0 when it's at the bottom.
Yeah, it kind of depends. Now, a lot of these problems, they get a little sloppy with the language, and we're going to run into some here, where they'll say a ball, but maybe it doesn't give you the dimensions of the ball. Okay? Now, for that, you would have an extended object of this ball, but you would use the center of mass of the ball, which would be in the very center. So the h for that would be right to the center of the ball.
So it wouldn't quite be 0, but it would be close to the bottom.
Right, and as long as you measure to the center of the ball, you're okay. If he just gives you some generic ball, he doesn't tell you what the dimensions are, you can kind of assume that it's virtually as small as you need to be. If there's any question, you definitely go up and ask him if he means you to take that shortcut. And I'll have some examples where we kind of take that shortcut along the way.
As a general rule, always err on the side of finding the center of mass.
Yeah. If you want to get the potential energy of the stick, you say, where's its center of mass? That is the H for MGH. So piecing this together with that in mind, the final energy, well, we've got some kinetic energy now. It's spinning. And it's going to be 1/2 I omega squared. And we just got done looking at the moment of inertia of a stick rotating around its end. That's the 1/3 ml squared. But its potential energy is mgh, and its h is L over 2. So again, that's the tricky part. Then we can set initial energy equal to final energy. We've got that potential energy. We've got this kinetic energy. You can take a look at the math. We're just missing this omega. That is going to be the angular speed that this is spinning down. However, he asks for what is the velocity of the tip of the meter stick just as it reaches the vertical. As it swings down, all these pieces are traveling different velocities, just this piece. But once I have omega, I know that the tangential velocity at the very end of the thing is omega times L. That L is for the meter stick. And then I've got my tangential velocity. So again, you don't need to get into this complication, but you do need to understand that we're talking about the position of the center of mass when we're doing potential energies. Okay? Now, he's done this problem a number of times in different forms. Here's another example where it's kind of pretty much the same problem, and let's kind of look at that. He takes a couple of, let's see, two meter sticks and 2 discs, and he does give you the radius of the disc, so we want to be a little careful that we don't take too many shortcuts here. The figure starts in the inverted position. This picture is a little confusing here. At the very bottom, it's going to rotate around this point, and then the idea is we've got a meter stick here, we've got another meter stick glued on the end, and then right at the tips of the meter stick were going to be the centers of the circular discs that we put on there. I've got this whole thing drawn as it swings up here. It looks, it's this thing just rotated up 180 degrees, so it's up on top. That's where it's going to start, and we're going to release it, and it's going to swing down here. So, and then he wants to know what is the angular speed at the moment that this thing swings down and is vertical. So you can see that it has a great deal in common. I chose the first one where we were just dealing with the meter stick. Here we've got a bunch of things going on here. Now, what we're going to need to do the problem, we're going to need to know the moment of inertia around this point of rotation. And this is a good example how we can start to put this stuff together. The idea that all of these things, I've got 2 sticks, they're both rotating, as well as 2 discs, so I've got 4 things that are going to have some contribution to the moment of inertia. So if we start with the very first one, I1 would be this stick that's hanging. It's going to rotate around the end point. We could just go ahead and use 1/3 ml squared as long as we know that. This is the mass sub s of the stick. And then the other stick that is off at this angle. Now this is kind of strange that it's off this way. It's going to come around here and be up here, and it's going to swing around like this. So it's not swinging about its end. It is rotating around this point, and so we need to use the parallel axis theorem to get the moment of inertia of this stick that's going to hold the discs. So we start off with, this is the moment of inertia of the rod about the end point, or excuse me, about the center of mass. We need that for the parallel axis theorem. And then we're going to move the axis here from the center of mass of that thing, which would be right here, up to point P, which is going to be a distance of L over 2. So that's the mass of the stick times L over 2, and we're going to square that. So that's the two sticks. We also have a couple discs that are on there. And again, we're going to say that these discs, as they rotate, they're going to be rotating around this point, not around their center. So what we can do for these discs, we can use the parallel axis theorem again. We say the disk is 1/2 mr squared plus the md squared. The d is the distance from that point of rotation to their center of mass. So this is d here. Hopefully you can see that. So it's going across here. It's on a diagonal. So the d is going to end up being root 2 over 2 times L. Let's see, did I have it'd be nice to break that down a little more. I've got L over 2 plus L over 2, so I've got two of those, root 2 over L. And convince yourself that this is going to be d squared. I've got one disk, I've got two disks, so I end up multiplying by 2. So kind of doing the math here, I end up with doing some simplification here as best I can. We have, this is 2/3 m L squared for the sticks, and then the disks are going to end up being this. Kind of go through this on your own, see if you can come up with these numbers. And then we can crunch the numbers as they've been given in the problem here and come up with the moment of inertia of this thing as it rotates around point P. So this problem is a great one to see how we can start to assemble things based on their individual moments of inertia and how we'd add them and build this collective device that's going to have this moment of inertia. So that part's kind of a separate problem, kind of messy. And then we're going to use what we had done on the previous problem using the energy principle. Now, one thing that's nice here, that we'll deal with the potential energy of the whole system, and the center of mass of this whole thing is, you can see from just symmetry, has got to be sitting right square in the middle. And that center of mass is going to come down. It's going to swing down till it gets to here. And so it is really just the change in the center of mass of the system. So let's get in here and use some energy. Note that the center of mass falls 1 meter. This is a meter stick. It falls 1/2 meter and another 1/2 meter, a full 1 meter as it swings down to here. And I suggested we can put our 0 for potential energy wherever we want. I suggested to let U sub G equal to 0 at the top, just for fun. We'll start up here at, let's see if I did what I said I did. Okay, at the top, I believe I did that for the center of mass. Let's see that. So making this 0, it's going to swing down to here. So let's take a look at this. The initial energy should be the final energy. Oh, I'm making both of the kinetic 0 and the potential energy of this thing 0. So I made this my 0, meaning it's going to drop down to here. If you want to do the problem and call 0 here and then start off with some potential energy, that's okay. But I just made that 0 in this example. Then we're going to have some final kinetic energy, and we don't want to forget that final gravitational potential energy. So again, as it gets moving, that should be 1/2 I omega squared, where I about point P is this complication, but I've got it reduced to a single term here, comes in here. And then minus the potential energy is going to drop. If I made this 0, this is down here in the negative. And I'm going to do this for the center of mass, so I don't have to do these individually. I can say as a system, the center of mass is here. So that's a great help as far as the change in the potential energy. I've got all of these things. I've got 2 disks plus 2 meter sticks is the total mass times g, and the distance that it's going to fall is going to be 1 meter, and so it's going to be down there. And I can take the negative term over to the other side, and we can go ahead and solve for omega final, and you can do the math and come up with 6.6 radians per second as this thing swings through the vertical. That omega refers to the angular speed of the whole object, so we don't point to a particular point on that. We just say the whole object is rotating with this angular velocity. Okay.
And would you get the same answer if you reversed it and said you got gravitational potential energy of 0 at the bottom?
Yeah, not a problem. The only thing that's going to change is that this would go over to the other side, and you could this would go over to the other side. Well, this would go as a positive over here on the initial side, so it would be up there, and then over here this would go down to 0. So the idea that it could be a positive term on this side, we take it over to this side, it ends up being negative. But you will get exactly the same answer. It does not matter where you put your 0. Okay. Okay, another energy thing. If we've got something. Okay, how are you doing? This is, yeah, intense stuff here. The idea of rolling without slipping. This often gets done with problems. The idea that it's rolling along a pavement and it doesn't slip or skid. If it's rolling, if we look at just, we say an instantaneous look at the motion of this thing, for any given instant, the point of contact here is going to be at rest relative to the road. If it wasn't, that's a case where the tire is slipping on the road, and that's a skid. So the idea that this disc is really rotating, if it's rolling, it's really rotating about this point of contact here. And imagine that it's going to, as it rolls, it's going to move through a small angle. I do want this kind of differential in that obviously as this rolls along, point P would change to another point at another instant, and it's going to be changing. But at this particular instant, and the way it's moving, it's going to sweep through some angle. And different parts of the wheel are going to sweep through different angles. We're going to primarily be looking at the center of mass. Out here on the edge of this thing, as this thing rolls, it's going to move through a greater distance than this arc on the center of mass. This gets used in problems. If you recall that plank that was on the rollers and it was rolling, the idea, if you've got something sitting on top as this thing rolls, it's going to move with a greater speed than the center of mass of the wheel. So this is, if you can kind of see this, you can sort of make sense of what's happening there. That was a homework problem, and I'm not going to get into that, but it's a good point to point that out. In fact, yeah, the idea of the velocity of the center of mass, if this is rotating around point P with some omega, R times omega would be the velocity of the center of mass moving. So this whole thing is going to be set into motion as it rolls along. It's not just spinning on a fixed axis. And so what we want to do is, if we want to look at, let's say, the kinetic energy of this thing, that's going to be 1/2 the I about point P, because that's what we're rotating, times omega squared is the angular velocity around that point. Now, what we can do is use the parallel axis theorem. The I about point P, since we're used to using the disk around the center, not around an edge point, I can say the I about point P is equal to I of the center of the mass plus mr squared. This is just md squared, and d is just the distance from the center of mass to the point of rotation, which is the radius. So we've got that. And then we can expand this a bit here. We'll take the 1/2 I about the center of mass, omega squared, plus I'm going to have a 1/2 we're going to m over r. If I bring the m squared times r squared, that's going to be v squared, and that's going to be a term also here. Now, we can think of the rotation, and this is very handy when doing problems, when you're dealing with rotating or rolling action, is we can look at this first term as being the rotational kinetic energy. Okay, that's relating to its rotation. And then 1/2 mv squared is as its translation. So think of this instantaneous rotation as being one of two things. It's going to be an angular velocity that's going to be rotating around its center as though it's not even just sitting there in space. And then this whole thing is going to start to move in the translational sense. It's going to pick up some velocity in the center of mass. So think of these as two separate energy entities. The rotation about the center of mass, that's the rotational kinetic energy, and the 1/2 mv squared is the translational kinetic energy. This is going to be something we'll be using more kind of indirectly, but it's good to kind of see where this stuff comes in and plays. Okay, so how do we get something set into motion? We need to, if we want to get something rotating, we need to apply something that's called a torque. And I think first looking at the idea of torque, I think the simplest way to look at it is kind of just on the practical level. You got maybe a stubborn nut here, and we've got a wrench on it. And with that wrench, if you want to turn this thing, apply a torque to it, you need to apply a perpendicular force to the handle. And the more torque you're going to get is going to be dependent on that force, as well as this lever arm. We call this well, let me just call it the lever here. And this is going to be, so the torque is going to be equal to R times F perpendicular. And hopefully this makes intuitive sense. I guess I got a capital R here. I got a lowercase here. I mean the same R. This is the most intuitive way of thinking of torque. Then we also have that a lot of times the force isn't always perpendicular to the handle or the rotation of this thing. It goes off, let's say it goes off in this direction. That force, just in an arbitrary direction, can be broken up into two components, one that's perpendicular and one that's parallel. And this parallel component just wants to kind of pull the wrench off or turn it around, push it on. It doesn't lead anything to, it doesn't have anything to do with the actual rotation of this thing or any contribution to the torque. So if we have a general force, and we typically talk about a theta, we say R goes out to this point of application of that force. And if we take that R and put it tail to tail with the force, the R would be along this direction. There's going to be this angle theta that we use to talk about this angle. If we look at F times the sine of theta, that would be this side or the perpendicular component. So a little clearer look or more general look, we take this basic idea, this perpendicular component is just F times the sine of theta, and so we can use this as a more general expression. And most of the problems you're going to be dealing with are this way. The book does introduce a vector cross product, and we won't be doing a lot with this. If you've seen it before, and Dr. Young has probably talked about it a bit, most of the stuff we're going to be dealing with is going to be kind of in the plane of the page. If you get into 3D problems, as you will later with your engineering classes, you will want to use the cross product. It becomes a very powerful mathematical tool. There's another way of getting at torques, which I'm going to save as we get into statics. This is just another way of calculating it. Right now, I think it's most important to have this idea that the torque is this idea. You're going to use this thing to get something to rotate. So let me go to that application of the torque, and we'll revisit this a little later. So let's go back to, let's say I've got this steel plate again, this kind of thing with an axle here. And imagine I'm going to like weld a nut on there, and I'll put a wrench on this thing. So the idea is, how do I get this thing to start to rotate? So I can apply this force. It's easiest just to put it perpendicular to the handle. As I apply that force, I'm going to start to get this thing to move. Now, this torque that we're going to apply, this net torque is just going to be R times F. The K hat indicates the direction. This comes from the cross product. Is going to be pointing out of the board. And as far as the meaning of that, if you're trying to make sense of that, it's going to be pointing this way. It points along the axis of rotation. And so using the right-hand rule, if you are using the cross product, it's going to be pointing this way. It points it along the axis. Again, you don't need to worry about this so much. We'll be dealing primarily with just the magnitudes. Now that net torque, R times F, gets applied to all of these. In a sense, it's kind of a lever-like action. As I put a force here, that force gets distributed to, not equally, but gets distributed to all the pieces. And it does in such a way that this whole thing, because it's a rigid body, are all going to start to rotate together. So the net torque is the sum of the individual torques. There's going to be, this force is going to have some F sub I on this one. It's going to F sub J on this one, F sub K on this piece. And of course, we'd be integrating all of this if we were going to turn it into a calculus problem. But this net torque should be just R times F. We can use Newton's second law and say, well, F of the ith piece is the mass of the ith piece times the acceleration of the ith piece. And I do expect that acceleration would be tangential, since that force is going to be in that direction. All of these forces should be at right angles to the radii. That's the direction it's going to start to move as it accelerates. And again, we're going to accelerate this. That force is F equals ma. Also, the acceleration, all these accelerations are not going to be the same value, but those accelerations are going to rotate with the same angular acceleration, since it's a rigid body. And the ith piece is going to be R sub I times alpha, would be that acceleration. We can bring that in. Then, well, we've got a pattern here. This R sub I times alpha, along with this R sub I, we can collect terms. One of these, alpha, is the same for all of them. That's, again, the importance of using these Greek letters and these rotational terms. I can factor out alpha, since it's the same for all of that. And then I'm left with m sub I and an R sub I, and an R sub I is an R sub I squared. And we've seen this pattern before, right? Okay, we've given it a name, and we call that the moment of inertia. So we can see that the net torque is going to be equal to I times alpha. Okay, let's think about that compared to Newton's law, F equals ma, where the mass is the mass of the object. Rotational terms, it's I. In terms of the acceleration, in the rotational sense, we're talking about alpha. The torque is a way of something analogous to the force. So we've got, instead of F equals ma, we're going to be using torque is equal to I alpha. And so be using this in some problems. Ultimately, these torques do come back to a force here, so we're not really inventing anything new. We're just kind of breaking the problem down differently, and hopefully we can use that to solve our problems. So this is another example. Okay, let's do another example here. Okay, this is very similar to one we did earlier. Earlier we dealt with this mass, and this fell a certain distance, and we used energy to get the rotation and get the motion of this thing. Now let's do it using forces and torques. We've got this disk is fixed on an axis. There's a hanging cord, remember, that was wrapped around it, connected to this mass. And we're going to let this thing go, and it's going to start to accelerate. Now, we want to start off with some kind of sign convention here. We're going to have the rotation of the disk as well as this mass is going to be falling. I'm going to give a sense of direction. I'm going to assume, obviously this is going down, so I'm going to assume plus is this direction. I've got to make sure that I also apply it to this. Here a lot of times people would say, oh, I want to call up positive. There are a lot of ways of doing it. You can make that work, but I think the best way is to say, if I call rotation this way is positive, this is positive going down, and then we can go ahead and look at that. So the torque applied to this thing is going to be T times R. Now, talking to people in the lab, I think Dr. Young is, a lot of people are using the kind of formalism that rotation this way is positive or rotation this way is negative. You can do that if you want. I think it might be better to do this as an absolute value, and so just deal with it positive. And the fact that I'm calling this the plus direction to match with this, I think is the best way to avoid problems. So I would just say the magnitude of the torque is T times R, and it's going to be equal to I times alpha. And the alpha would be positive if it's going in the direction I'm calling positive, and negative if it's going the other direction. And there'll be a point on the rim that is the acceleration, which is going to be r times whatever alpha this thing is rotating with. Probably should have said a sub t there. It's the tangential acceleration of a point on the rim. And that acceleration should match with the acceleration of this mass. Okay, now let's kind of be a little careful. Let's put this together. Let's focus maybe down here as the most comfortable place to start the problem. I'm putting, there's going to be two forces on it, mg and t. That t is going to be applied up to the disk, so you can see how these are action-reaction. These are paired forces, coupled. And we're looking at this one, calling down positive, that mass is going to be, the force is just mg minus the tension should equal the mass of this thing times its acceleration. Or I can solve for the t. I have a couple unknowns. I don't know t and I don't know a. It gives you some dimensions here as far as the mass and the size of these things. Then I'm going to want to be able to take this torque back up into this equation here. So again, the absolute value of the torque applied to this thing, I'm going to call this the positive direction, is going to be T times R. It should be equal to I times alpha. I can say take T from this expression and substitute it in here. And I do that, and then what often happens in these problems, the I is that of a disk, so 1/2 mr squared, and the angular acceleration is the same as a over r. Okay, a was equal to r times alpha, or alpha is equal to a over r. This r will cancel one of these. This is an r squared. And this r on this side will cancel the other one. So you actually get rid of your r's. And it gets a lot simpler, more friendly looking here as we look at mg. I'll take this minus over to the other side. And we have mg, that force, is equal to m plus 1/2 of big M, which was the mass of the disk, times the acceleration. And solving for the acceleration, we get that. If we want to get the angular acceleration, we can take that a and divide by r, and we can come up with that. He does ask for, what does he ask for? What is the angular acceleration of the cylinder as the mass unwinds? So that would be how that's done. So these are just some basic problems here. Let me just see where we're at. Maybe, how are you doing? Do you want to take a break now, or can you hold on for a little bit? Let's, okay, we just looked at this one. Okay. No comment, or you're just totally shell-shocked? Okay. How many, you're feeling pretty comfortable with this? And I hope? No? Nobody's? Okay. Everything's shaky. There's a lot of stuff to keep track of. That's one reason I released these notes, so you can go back and replay this stuff. I know I'm kind of jamming through this pretty fast. Hopefully you're kind of picking up the big picture, and then as you go in and study, you need to break these things down and try them for yourself. This is a problem very similar to what we have done in the past. We have a kind of an incline. We've got a couple masses here that are connected with a string, and it's over a pulley. This is no longer what we used to say before as a massless, frictionless pulley. This pulley has some mass to it, so it has some inertia, and it's going to be included in the problem, along with these two masses. If we break this up into free body diagrams, these guys should look familiar. This guy would be down here. We'd have gravity pulling down on this thing. We've got a tension pulling up. That tension is going to get applied to this pulley here. You may be noticing I'm using some subscripts. Let me get to that in a moment. I've got this guy, we've got some tension in this cord pulling up. Gravity, of course, is down. Along this sense of motion, I've got a component of gravity. mg times the sine of theta would be the thing that's trying to pull this thing down. On the part that's kind of new to us now is we're applying these tensions to the pulley here. That this is going to be a big disc that's going to be rotating. It's got mass to it. And in the past, we've always just called this T. For a massless, frictionless pulley, it's no problem. We can have the same tension. All this thing does is deflect. We've got a little different case here that if these two T's are the same, is this pulley even going to rotate? If T1 was equal to T2, would that rotate? Yeah, right, it would not rotate. We need to get it to rotate. Now, I'm having a sense of sign directions. I'm saying this whole thing, this whole system is going to move like this, or if it does, I'm going to call this the plus direction. Means this thing's going to go down. It's going to pull and want to rotate the pulley this way. This thing, we've got this tension on this other side, wants to pull this mass up, calling this the plus direction. Gravity is fighting that, having a component in the negative direction. This T1 wants to get this thing to rotate like this, wants to rotate it in this direction. This T wants to rotate it in the other direction. To do the problems, we need to join these and do these, so it's a good idea to choose a plus direction. I chose plus going up, coming like this and down. If we end up doing the math and we get a negative acceleration, it's just going the other direction. So the math will tell us that. So I've got these two blocks. Now, again, in the past, we would just say, well, m of the first one, that's going to be this T1, and then mg sine theta is the component coming down. We can do something over here, m3, the same thing. Down is positive, so m3g goes positive. minus T2 is equal to m3, that mass times the acceleration. So this part is the same, and we could do the problem if T1 is equal to T2. That's what we had done in the past. Here I'm keeping this separate. So I'm going to take each one of these. I'm going to solve this one for T1, this one for T2, and then I'm going to go into the pulley. Now the pulley is kind of the new part here. This is going to be, instead of the sum of the forces equal to ma, this is going to be the sum of the torques are equal to I alpha. The sum of the torques are going to be, if this is the plus direction, T2 wants to get it to rotate that way, and I'll call that positive. T1 wants to rotate it the other way, call that negative. So I've got a positive torque wanting to go that way, negative torque going the other direction. And this is kind of following the sign convention as you would do like in a math class. And then that should be equal to I. The I is the moment of inertia of the disk. Alpha is going to be A over R. You'll see a lot of these patterns as you do problems keep repeating. This R is going to cancel with one of these. I can factor out an R here and cancel the other R, and so I'm left with just T1 minus T2 minus T1 is equal to 1/2 M2 times A. I've got M2 is that mass of that disk. And then we can, since I'm going to substitute these in, I can go ahead and do that and do the math. And we should come up for the acceleration. I've done it all kind of symbolically here. I think it's easier to see this unfold. Then when you actually use these figures that he has, the radius and mass of the disk, in this we can go ahead and solve for the acceleration of that system. Okay. So this is something to think about. Okay, I'm going to come back to this one. This is a more difficult one. I put it on the extra sheets. Yeah.
Could you go back for a second?
Yeah.
I have a question about the initial setup.
Oh, went the wrong way.
When you have T1 minus mg sine theta, why is it minus mg sine theta, not just minus mg again?
Excuse me, where are we here?
For M1?
Oh, for M1. Oh, okay, the forces on that.
Yeah.
Okay, we've got T1 pulling up. We take M1G. If this is at angle theta, that should be the same as this angle. That's going to be theta. Do you see that? Or okay, and then if we take M1G times the sine of theta, that would be a component that's in that direction. Okay. Going down the incline, so that would go in as a minus. So, yeah, the T1 minus M1G sine theta. Okay. Yeah, little things, the sign conventions, the little signs can really mess you up. That's why, again, I like to, and I think it works best for most students, to go ahead and label like the plus direction for all of these things, and then go with that as the convention. As far as rotation, a lot of people are kind of set to, well, this is plus rotation, the other direction is minus. It's a lot like choosing your x and y axis being plus or minus in either direction. It really doesn't matter. The idea that this torque, if I'm calling this a plus direction, any tension or in turn torque that wants to get it to rotate that way I'll call positive, and T1 would be wanting to get it to go the other direction, I'll call that negative. So tricky things. It's easy to mess up a problem just because we are taking these things from one equation into the other equation. We need to be consistent in the problem, and we need to be consistent in terms of the sign convention.
How do you know which way the system's going to move?
Oh, a good question. It all comes down to this. And if I don't know what, he gives us this, and so when we actually solve this, I get a plus here. Now, if I happen to get a minus, I don't have to start over again. That just indicates it's going the other direction. So if I get a minus acceleration, I'd say, oh no, this one's not going down, it's going up. This one's not rotating this way, it's rotating this way. And this one, instead of going up, is coming down the incline. And you can kind of even see that maybe here you've got m3g minus m1g. So if this term gets to be bigger than that term, that minus sign is automatically going to make everything negative. So yeah, the math is going to tell you that.
So the acceleration would be negative, so in terms of getting the correct answer, would you just switch it to a positive in that case?
Yeah, he would be totally cool with that. If you come up with a negative, maybe you want to put it in words that, you know, if you wanted to know, let's say, what the acceleration of this block is, you'd say it's a negative or it's going up, so something. But yeah, don't start over again with it and say, oh, I got to get out my eraser and turn everything around. He'd be totally cool with that, and he would know whether you're interpreting that minus sign correctly. So, okay, why don't we take a little break? I know I'm jamming this stuff at you. We've got a lot to go. Why don't we take about a 10-15 minute break, and then we'll come back. I'll leave this problem up here. We'll come back to this one. This is one of the more difficult ones. I've got this in along with the extra problems for the problems that you can take a look at as far as past exam questions. All of these are past exam questions, so it's a good idea to take a look at these. So let's do that, and let me just take a look ahead. Oh, and then we'll start angular momentum. So we're just about, we'll be getting into rotation, and then we can start to do some problems where we start to put it all together. So, scary. Okay, I'm sure glad I don't have to take the exam for you. Okay. So again, we'll come back in about 10 minutes. If you want some coffee over there,